Okay, so today I'm going to cover two sections in the book. I'm going to cover section 1.5 and I'm also going to cover 1.6. Both of these deal with infinite limits. 1.5 is actually limits where the output is something of an infinite form, and 1.6 are things where we're approaching negative or positive infinity with x. Let's start off here. I just took this function 1 over the quantity x minus 1. I started with this function because I think we all know what that looks like. Just think of your 1 over x function shifted one space to the right, okay? So I went ahead and made a table using my calculator. You folks can do this as well. In a case like this where I want to enter values and I don't want to have it on a scale, go with the ask mode versus the auto mode. That way you can just plug in whatever numbers you want and sort of experiment with what's happening. Okay, so what we're going to look at is we're going to look at the limit as we approach 1 from the left, okay, and the limit as we approach 1 from the right. And so as x approaches 1 from the left of f of x, we're starting off with the values coming from the left, so that is less than 1. So as I get closer and closer to 1 from the left, you can see what's happening. So we start at negative 10, negative 100, negative 1,000, and then we're up to negative 100,000. Now, this is not like regular limits. This does not mean that our limit from the left is negative 100,000. If I went even closer, like if I went 0.999999, you would see that this number is going to be a larger negative number. And we can keep going on like that as we get closer and closer to 1. And I encourage you to sort of investigate that. So get closer to 1 from the left with your calculator. See what it's going to. So this, we would say the limit as x approaches 1 from the left of f of x is equal to negative infinity. Okay? So what we see is the y values growing without bound in the negative direction, which would indicate negative infinity. Okay, now let's look at this thing from the right. Now this does happen to be symmetrical at x equals 1, but let's just sort of once again confirm this. So as I approach 1 from the right, we see the same type of thing. So 10, 100, 1,000, I'm up to 100,000. And I can make this number get as high as I want, actually, just as I get closer and closer to 1. So if I wanted that to be a billion or a trillion, or even something larger than that, I can get there by getting closer and closer to 1. So we say the limit as x approaches 1 from the right is infinity. Okay? Now, once again, just like when we, so these are different creatures, these limits that go to infinity. So one thing I'll say once again is, just like when we started defining limits, in this class we're not going to get into the strict classical delta epsilon proofs. We want to understand what this means intuitively. So I'm going to write that up. So if I say the limit as x approaches a certain value c of f of x is equal to infinity. And here we're doing right from left, but you know, c would mean from both sides. What this means is as x gets closer and closer to c from either side, so here we're doing left and right limits, f of x grows without bound. And either in the negative or positive direction. Well, if we're doing infinity, that would be in the positive direction. We'll just leave it like that. If we say the limit as x approaches c of f of x equals negative infinity, you would grow without bound in the negative direction, or let's say decreases without bound. Okay. Now, once again, just like limits, we don't have to define this very technically, but if you think about it, if I say the limit's going to infinity, that means that we can get this function to spit out as high number as we want. So we could play this game where you choose the output you want and I will get it there, depending on how close we want to get. So you could investigate that. This one will be easy to solve algebraically, but that's something that I want you to keep in mind when we say something goes to infinity. We can get that to go to whatever number we want. It's very, very important in this class that we realize that infinity isn't a number, okay? It's a concept. So even though we would say this limit is equal to infinity, this is not like saying the limit is equal L. When I say the limit is equal to L, I'm saying that limit exists as in it equals a specific number. The limit going to infinity, we would still say the limit as x approaches c of f of x does not exist because it doesn't equal a number. So for instance, if I'm talking about continuity and things like that, which we talked about in the last section, we would still categorize an output going to plus or minus infinity as the limit not existing. Okay? All right, let's move on. Okay, so let's return to the function that we saw in a tabular form, f of x equals 1 over x minus 1. But this time, let's look at the graph. We all know, and we've been discussing these things since Algebra 2, we all know that this particular function has a vertical asymptote at x equals 1. Typically, if we have a 0 in the denominator that we cannot algebraically remove, typically that means it's going to have a vertical asymptote. There are some cases where there's a 0 in the denominator, it can't be removed, but it's a step, which we'll see a few functions like that, but most of the time we're talking about a vertical asymptote. We've been talking about vertical asymptotes for years. Now we're actually going to define it. So the actual definition of vertical asymptotes deals with limits that go to infinity. So the strict definition is if the limit as x approaches a from the left of f of x is equal plus or minus infinity, or, and I guess this is and or, the limit as x approaches a from the right of f of x equals plus or minus infinity, then f has a vertical asymptote at x equals a. So now this is a strict calculus definition. So if you're ever asked to say, prove that something has a vertical asymptote at a particular place, for instance, if I want to say that this has a vertical asymptote at x equals 1, I would actually need to say that, well, the limit as x approaches 1 from the left of f of x is equal to negative infinity. And by the way, that's enough. Once I have one side, I know there's a vertical asymptote there. Frequently, with typical rational functions, we do see this scenario where from the left it equals positive infinity, from the right infinity. Sometimes both sides will go to infinity, or both sides will go to negative infinity. It doesn't make a difference as long as it happens on one side. Frequently happens on both, but it doesn't have to. So for instance, if you think of y equals ln of x, or any log, right? This has a vertical asymptote at x equals 0, right? So this has a vertical asymptote at x equals 0, okay? And that is because the limit as x approaches 0 from the right of ln of x is equal to negative infinity. It doesn't have anything going on the left, of course, because the domain of ln of x has got to be strictly greater than 0, okay? But we just need it on one side, all right? Let's talk about the difference between holes and vertical asymptote when we look at things algebraically. Okay, let's talk about holes versus vertical asymptotes. What I'm about to say deals with typical standard algebraic rational expressions. It doesn't pertain to things that have transcendental functions like e to the x, sine x, etc. And I'll talk a little bit about that in a moment. But algebraically, when I look at this, it's a pretty simple thing to see whether it has a hole or a vertical asymptote. With typical algebraic things, we get both holes and vertical asymptotes when we have zeros and denominators. The question is whether or not we can remove them or not. So for instance, in this particular case, I can factor this thing in the denominator, factor out an x, I get x plus 2. Now what I see is I can cancel the x's. Now let's be clear, these are not the same functions now if I cancel these out. So if I can remove the 0 in the denominator algebraically, and I use that word remove because it has some pertains stuff dealing with continuity. So if I can remove the 0 in the denominator, then it's going to be a hole. So in this particular case, we have a hole at x equals 0. It's still not part of the domain. It's still discontinuous there, but it's what we call a removable discontinuity. And with a hole, of course, the limit is still going to exist. So we can still find the limit as x approaches 0. It's going to be 1 over 0 plus 2, which is equal to 1/2. So the limit still exists. Okay? If we can't eliminate the 0 or remove the 0, for instance here, we are going to have a vertical asymptote at x equals negative 2. And that is because we cannot remove the hole, or excuse me, remove the 0 in the denominator. Okay, so we're going to have a vertical asymptote at x equals negative 2. And we would say the limit as x approaches negative 2 of f of x does not exist. Keep in mind that in this context, when we're talking about continuity, a limit going to plus or minus infinity does not constitute a limit equal L. It's important we understand that infinity is not a number, okay? So vertical asymptote at x equals negative 2 because I can't remove it. And it's basically that simple when it comes to standard algebra things. So when we're getting in this discussion, does this thing have holes? Does it have vertical asymptotes? Look at the zeros and the denominators. If you can remove them, if you can find a way to remove them, it's going to be a hole. If you can't, it's going to be a vertical asymptote. Now, if you're dealing with functions like, and I'm going to talk more about this function here in a moment, but if I'm talking about a function like sine x over x, okay, you look at that one and go, oh, I got x in the denominator, there's nothing will cancel with that. That means I have a vertical asymptote at x equals 0. That is actually not the case. You have a hole at x equals 0. Down the line, we'll learn how to deal with things like that. Right now, we can't. Okay, so that basically does it for 1.5. We're going to go on to 1.6, which is just limits as x approaches plus or minus infinity. Okay, so now we want to look at situations where the limit as x approaches plus or minus infinity. What does that output go to? So once again, I generated a table using the ask feature in my table set on my graphing calculator. I entered this function. I want to do this function because it kind of gives us a look that we don't always see with limits to plus or minus infinity. So what happens if I want to see the limit as x goes to infinity, in my table I'm going to plug in larger and larger and larger and larger numbers, and I'm seeing if this is tending to a value. And when I plug in these larger and larger values, it becomes very, very clear that this thing is getting closer and closer and closer to 0.5. Once again, and I'll talk more about this in a second, since this idea of limit This thing may or may not equal 0.5. It actually could equal 0.5. That's another thing I'm going to talk about. It could be that it gets to 0.5 and it stays there. Most commonly, it's going to ever approach 0.5. It won't quite ever be exactly 0.5. But once again, we want to, this idea of limit means that we can get as close to 0.5 as you choose. So if you want 0.4 and a million nines, something very, very close, there is an X value that will get you there, okay? So as X gets larger and larger and larger, we're tending to 0.5, okay? So our limit as X approaches infinity of f of X equals 0.5. Not the 0.49999, which sometimes people will put, no, this thing's getting closer and closer to 0.5. If you aren't convinced from that, then just keep going with higher and higher numbers. At some point, your graphing calculator will get to the point where it'll actually round it to 0.5, even though it never will actually be there. Okay, so now we're going to do the same thing as we go to negative infinity. So we're plugging in larger and larger and larger negative numbers. These should all be negative, my apologies. So we plug in larger negative numbers. And once again, what we see is as this number grows towards the negative direction without bound, our y value in this case looks like it's getting closer and closer to negative 0.5, okay? And then once again, if you weren't convinced there, you could go higher. You could go negative 1 million, negative 1 billion, et cetera, et cetera, et cetera, and you will see that this gets closer and closer to negative 0.5. And once again, we can get it as close to negative 0.5 as we choose. I want to show you this one because we see that the horizontal asymptotes are different. A function can have literally an infinite number of vertical asymptotes, but at most it can have is 2 horizontal asymptotes, otherwise it wouldn't be a function. So you can have one in one direction and one in the other direction like we have here, or you can have both in the same, both the same value in either direction, or you could have a function that's just one-sided, like if you think of your exponentials, they go to, like y equals e to the x, looks like this. It approaches 0 as we go to negative infinity, but to the right, it goes to infinity. Okay, so anyways, if I actually graph this is a pretty peculiar function, and it looks something like this. So if this is 1 and this is negative 1, it looks something like this. Okay, and in the other direction, it looks something like this. Okay. Now, one thing you probably already see here is a limit that tends to, as we go to plus or minus infinity, that tends to a value. Well, what is that? It's just a horizontal asymptote. And just like we use limits that approach plus or minus infinity as being the definition of vertical asymptote, the same is true for horizontal asymptotes. Okay, so let's talk about that. Okay, first of all, I want to put the definition that we'll operate under for a limit as x approaches plus or minus infinity. I just did the positive side. To the negative side, it'll be the same, except it decreases without bound. So when I say the limit as x approaches infinity of f of x is equal to L being a number, not plus or minus infinity, what I'm saying is x grows without bound, larger and larger numbers. F of x gets sufficiently close to L. So once again, as close as we want to get to L, we can get to that L if we're saying that that's the limit. It's possible it gets there and stays there, okay? So, you just spit all over the board. And I'm going to talk more about that because that tends to cause some confusion with people, what people thought normally was horizontal asymptotes, because our definition of horizontal asymptote, once again, is using this as a limit. So vertical asymptotes is very simply as x approaches a particular value, if the output's going to plus or minus infinity, we have a vertical asymptote. Horizontal asymptotes are kind of the opposite. As x approaches plus or minus infinity, if the output tends to a particular value, then we would say it has a horizontal asymptote at that value. Now what that means is anything where this is true is a horizontal asymptote, even in a case where it's trivial. This is not anything you would have been taught in the past. And it tends to cause people some confusion. So if I give you the constant function f of x equals 3, okay, that actually has a horizontal asymptote at 3. Because if I take the limit as x goes to, and actually it doesn't matter what direction, it's the constant function, it spits out 3. So it's not getting sufficiently close, it is actually 3. So we would say that this particular function has a horizontal asymptote at y equals 3. All right? So this idea that asymptotes are things that the function will always approach but never actually equal is not in line with the definition. Now, typically with vertical asymptotes, that's true, because with a vertical asymptote, if it did actually get on that axis, it wouldn't be a function anymore. Okay? But with a horizontal asymptote, we're going to see that. In fact, I want to look at a pretty strange case of that here in a moment. Okay, I want to talk about this particular function, sine x over x. I've referred to it before. In this case, it gives us something that's quite strange. So what we see here as we plug in larger and larger numbers, and once again, if you're going to follow along with this, make sure you're in radians here. Always in this class when we're dealing with trig, we are in radians. But what happens here, you see that like at 10, it gives us a negative value somewhat close to 0. But at 20, it goes positive, and then it keeps doing this. So you see, and throughout it has negative and positive, and that's all the way to infinity. But it still has this thing where it's getting closer and closer to 0. Now, with that wording, let's be clear, since it's oscillating, there are times where it's moving away from 0. But there's a window that we can always get it into, and it fits that definition, because you tell me how close you want it to 0, and I can find an x value from that point on. It'll always be that close to 0. Now, what's very strange about this from our past experience, let me just give you a look at what this graph looks like, and I'm just going to do a rough graph. It has actually a hole here, and then it kind of goes like this, and it does this in both directions. It's symmetric. Okay, so it does this in both directions. Okay, it gets, even though it oscillates, okay, it does get to the point where it can get sufficiently close to our value 0. So if I say if I'm doing the limit here, I do say the limit as x approaches infinity, and actually negative infinity of f of x is equal to 0, even though it's ever oscillating. Okay, so now by the definition, we would also say, so this particular function has a horizontal asymptote at y equals 0. So this idea that a function does not ever sort of touch the horizontal asymptote is not actually part of the definition. It's what we see typically with rational functions that we saw in Algebra 2, but that isn't the case once we get into transcendental functions. So we do have a horizontal asymptote at y equals 0, but it's sort of different than what we normally see. So I just want to make you aware of that. Okay, now let's talk about how we actually find horizontal asymptotes or limits to plus or minus infinity. Okay, so now I'm going to talk about how we actually determine these things algebraically. Obviously, if we have a calculator, we can always use tables and graphs, but what if we don't? What if we have to look at the algebra for these things? So it's pretty easy when we're dealing with typical algebraic rational expressions. Basically, what you do is you take the largest things from both the top and bottom and compare them. Okay, so I chose 3 different ones that have 3 different situations. So the largest things, top and bottom, the largest terms, and we ignore the rest. So essentially, in this problem, when we're talking about large numbers, nothing matters but the most dominant terms, the fastest moving terms. So basically, you play this game. So I chose these 3 examples because they give you sort of the 3 different things that can happen. First of all, if they match, what that means is we're looking at the coefficients here. Now, if I look at these coefficients here, then I have -7 over +1, so this would be -7, okay? If I look at the coefficients here, if they have a higher degree on bottom, that means the bottom is going to infinity faster, so ultimately this thing's going to collapse to 0, And then finally, if we have a higher degree thing on top, more powerful thing on top, this thing is going to go to infinity, okay? Now, we do have to be careful with negative or positives. Now, if we're going to infinity, it's pretty simple here because we're just plugging in positive numbers. If we go to negative infinity, what we need to do is we need to plug in that negative value. So notice here, that's not going to make any difference because both of these are squared. So that's going to be -7 as well, okay? So if, and of course with 0, it never makes a difference because whether it's negative or positive. So for instance, as I go to infinity, what's happening is it's approaching 0 from the top of the graph because we're getting a positive 0, so it's coming from the positive side. If I go negative infinity here, we get a negative or a positive, so it is approaching from the bottom, right, from below the x-axis. Here, however, as I look, the limit as x goes to negative infinity of h, I'm plugging in a negative up top, right? That's going to give me a positive, so I'm getting a positive up top. I'm plugging in a negative at the bottom, that's going to be a negative. So a positive or negative, this is going to be negative infinity, okay? Now, those are the limits, and if they ask you for the limits to infinity, that would be it. If they ask you for the horizontal asymptotes, well, this would have a horizontal asymptote at y equals -7. This would have a horizontal asymptote at y equals 0, and this would have no horizontal asymptote, okay? So we're only going to have the horizontal asymptote when the limit to plus or minus infinity is a value, not when it's plus or minus infinity, okay? I want to give you a couple of other examples here that are a little bit different.